Okay, let's look at this problem. This is our first problem that contains a switch, and I want us to kind of slow down and look at this one carefully. This is the circuit as given, and I made things as simple as I could with the actual circuit. So we have a battery with EMF E, and then there are four resistors, and they're all identical. So they all have resistance R. All right. Um, because I want the notation to have a little bit more texture, I'm actually going to add some subscripts. But let's have it known that these resistors are all the same resistance, okay? But I'm going to add, just for ease of reference, I'm going to go ahead and add some subscripts to these that I'm going to refer to them as R1, just so I have an easy way to refer to each of the different resistors because they may or may not be doing different things that we need to talk about. Okay, so what we're being asked to compare first is the circuit in its current state as shown with the switch open, and then think about what's going to happen in this circuit, how it changes with the switch closed. So I'm just going to just do a little sketch of the circuit down here, actually, with the switch closed so that we can highlight and think about that version of the circuit as well. So this is these same resistors. The difference here in this particular orientation with the switch closed is that now R2, 3, and 4 are in parallel with respect to each other. Okay, so if you haven't yet thought about these questions that are posed in this problem, pause the video and go ahead and think about those questions and then come back. Okay, so you're back and hopefully you looked at the problem. A way that I would start doing any of this is thinking, of course, about potential. And if you've noticed a theme in these videos is that I want you guys to have potential as your primary way of looking at a circuit. So let's just go through with a highlighter and look at different values of potential in these two versions of the circuit. So first I'll just take yellow and I'll highlight yellow from the positive terminal of the battery in both cases. And I'm going to highlight blue from the negative terminal of the battery in both cases. And then I'll choose a different color. Up here, I'm going to choose green for all this. And down here, I'm going to choose something different because it might not be the exact same elevation as the green. So notice that the yellow and blue are the same between these two versions. Opening and closing that switch cannot change the potential difference of the battery. And the yellow-blue difference is the potential difference of the battery. So the yellow is the same. That can be the same color. Those are both up at E. The blue is both down at 0. Okay. And then the question is, right, there's this third level that is maybe going to be the thing that changes when you open and close that switch. And this is really how I want you to think about switches. It's tempting to consider switches as being all about the current, right? Like, oh, well, I close that switch and then that allows current through. That's not the most fundamental way or the strongest way to think about circuits. It's the easiest. I get that. But I'm trying to teach you a way that has more subtlety and is really a more robust method of understanding. So check it out. Let's look at the top picture with the switch open. And as you can see here, resistor 1 goes from yellow to green. So I'm going to have current, right? I have a potential difference. I have a potential difference over resistors 3 and 4 as well. They go from green to blue. They're wired in parallel. So check out resistor 2. Now, there's no current through resistor 2, right? That branch is broken, so there's no current. And so since there's no current running through here, there's no potential difference. So I can take this blue here, my highlighter, and go right up through there. All right. So if I look at the question down below, or I'm sorry, the scenario down below with the switch closed, Here I can see that R2, resistor 2, is dissipating, right? There is current going through it. It's heating up. It is dissipating energy from the circuit. Therefore, it has a potential energy difference, right? We are losing energy at that point in the circuit. Okay, cool. Now here the question. Let's go back to the question. So make sure that you really are understanding what's going on with the circuit before thinking about the questions. How does the potential drop over each resistor change when switch S is closed? So if you haven't yet done this, I want you to think about this. And a way you could do that is just let V1 be the drop over resistor 1, right? And I want you to think about, does it increase, does it decrease, or does it stay the same? V2, the drop over resistor 2, when you close the switch, does it increase, does it decrease, or stay the same? Same thing for 3 and 4. So again, if you haven't taken yourself through this, this is the whole point of the exercise. Pause the video here and choose one of those. For each of these cases, when you close the switch, what happens to V1, 2, 3, and 4? So go ahead and pause here. And hopefully you went through that exercise or you'd gone through it previously. Now let's talk through our choices here. So potential 1, maybe I'll leave that alone because that is one of the harder ones to talk about. Let's talk about potential 2, then we close the switch. So R2, when the switch is open, R2 has no potential difference. So you know that, once the switch is closed, it has this purple-blue potential difference. So V1 increased because it increased from 0, right? With the switch open, V1 was 0. Oh, no, I'm talking about V2 in that branch, sorry. With the switch open, V2 was 0. So V2 increases, and it increases from 0. Okay. V3 and 4, not sure what those are doing. Maybe you thought they stayed the same. Maybe you thought they decreased. Maybe you thought they increased. So let's talk about how we can figure out what they do. Now, I will say that what they do is not really dependent on the switch here, right? Because R2 is wired in parallel with those. But what they do is going to depend on the drop over R1. So when you close the switch, if the drop over R1 changes, and we know it does change because in this top picture, we're going from yellow to green here, right? As we go through R1, we go from yellow to green. And in the bottom picture with the switch closed, we go from yellow to purple. Like, I know purple and green are not the same. So we know that the potential over R1 has changed. The question is, did it go up or down? So different ways of thinking about this. The way that I really like is if you can see that when you close the switch, and you can show this in a calculation too, when you close the switch, you are decreasing the equivalent resistance. Let's say that again. When you close the switch, you're decreasing the equivalent resistance. You can do the math out and figure that out. When you decrease the equivalent resistance, you're now drawing more current from the battery. When you draw more current from the battery, that means my drop over R1 is going to be greater. And here I'm using V equals IR. So if I increase the amount of current going through a resistor, I've just increased the potential difference of that resistor. So that means that V1, the drop over R1, increases when I close that switch. I close the switch, my equivalent resistance drops. I draw more current from that battery and push more current through R1. Notice that R1 is wired in series with that battery, yeah? So I'm pushing more current through R1, greater drop over R1. And then I can look at 3 and 4 and say, well, guess what? If R1 increased, then 3 and 4 must have decreased because the stairs of R1 plus the stairs of R3 or 4, those are wired in parallel, must be equal to E still, right? If I think about that loop, my loop around here, I know that E minus V1 minus V3, say, must be equal to 0 as I traverse that loop there. Think about Kirchhoff. Okay, so I know that has to be true. So if I increased the value of V1, then V3 must have just decreased. So that's in V4, V3 and 4 are wired in parallel, so 3 and 4 had to decrease there. This question also asks us about the currents, and the currents are going to do the same things that the potentials just did there, as their resistance is the same, right? So I'll have current and potential proportional to one another. All right, and then the last part here is just asking us to find the currents here before and after closing S, and then that way you can actually see where there's more and less current in the circuit. And we can go over that if you want to. What I would probably do here is just find the levels, like find what the green elevation is and then find what the purple elevation is. So what we could do, I'm just going to get rid of this stuff here so we can have a little bit more space, is we can find the equivalent resistance in each case. In case you haven't done that. So let's do that. Let's call this, well, I'll just prime the case down here. That's all I need to do. So in other words, if the battery current for the top picture is I naught, I'm going to call the battery current for the bottom picture I naught prime. So the equivalent resistance for the non-primed case here is just going to be R1 plus, and then I have 3 and 4 in parallel, all to the -1. Okay. So this actually ends up giving me 3R/2. So my battery current is equal to 2E/3R for the open case. And for the closed case, I'll prime this case here. R equivalent primed is just going to be R1 plus, and now I've got all three of these in parallel. Remember that all the resistances are equal to R. I'm just using this notation so you can see where I'm getting these from. And then so this will actually be equal to 4R/3, and my current in the primed case is going to be 3E/4R. All right, so you can see that we're drawing it. We had you could think of like this 2/3 proportion in I naught and then a 3/4 proportion in I naught prime. So you can see that we're getting more current there. So that'll be the current through R1. That's the battery current. For the lower case, the bottom case here with the switch closed, that current is going to split evenly into these three branches. So that'll be any of the other currents here, I2, I3, and I4, they're all going to be the same in this problem because the resistors are identical. They're just going to be 1/3 of I naught prime. So that's just going to be E/4R there. Those are all those currents. And in the case with the switch open, we already found the battery current. The current through R2 is going to be 0 with the switch open. And then the current through I3 and I4 are going to be the same again because this is all set up proportionately, and it'll actually just be half of the battery current. So that'll be E/3R. And that's our currents.